Boom. Hello and welcome back to Calculus 3, section 13.4, triple integrals. Calc 1, right? Single integral. Calc 2, single integral. Now double and now triple. Are they going to be 4? No. Sorry for disappointment. This is where we end. Why? Because this is going to give us 4D already, right? If you think about it, we already have a dimension per integral, and then you put the function inside. It's going to be dx, dy, dz. That's 3D already. And then the function is 4D. Now, we talked about the concept of the 4D earlier, where you can think about the density or the temperature or energy, right? So it could be a state, right, that we can discuss, and we need the fourth dimension for that kind of concept. Now, the triple integral progress is going to follow the same route as the double integral. The first type we do is going to be the one that has just numbers all around, rectangular one, right, with just numbers. And that really computes the volume or the bulk of the box, like the one that we are sitting in, right? The next step in the progression is going to be to put functions in those limits, and that's going to give us all kinds of shapes and curves and things in space. And then we are going to go and put the polar coordinates in a base, where in 3D we are going to split off into cylindrical and spherical. So two sections of this stuff, it's going to follow the same pattern. So we start first with the rectangular region. And for the rectangular region, we are going to put the triple integral over the region D of the function f of x, y, and z. And then we have dv, right? Now, this dv is going to have the combinations of x, y, and z. So we have x, dx, dy, dz, dx, dz, dy, dy, dz, dx, right? So all of those combinations. There are 6 of those, right? So we can have all of that. Now, the first one over here is going to be f of, let's say, x, y, z, and I'm going to put in dz, dy, dx. Again, could be any other combination, because I want to go with a, b, c, d, e, and f. So a, b, c, d, e, f, those are just numbers. What this computes, again, if you have f inside, it's a 4D. If you don't have f, it just computes the volume 3D. So that's our first stop. I mentioned, 5,000 times so far. If you are tutoring, you are making money, right? So next time you are tutoring this, middle school kid and comes up with the box, and you guys are supposed to talk about the volume. Now, this box is 5 units long, 3 units wide, 2 units tall of something, right? To calculate the volume, clearly volume is 5 times 3 times 2, which is very good, 30. But then, see, this pesky child says, why? Ooh, let me show you why. The way we do this, actually, is we place this box in a three-dimensional coordinate system, x, y, and z. And in that coordinate system, we know that we can set up a triple integral. We are going to put 1 in here because we are looking for the volume. And then we can put whatever order we want, because order, just like in double integrals, doesn't matter. So let's put dx, dy, dz. It doesn't matter. Now z is the outer integral. and z is the height of 2, so 0 to 2. Y is the integral on the 0 to 5, and x is 0 to 3. So now when you integrate this, you have the double integral 0 to 5 of x computed from 0 to 3, dy dz equals 2. They are computed the same way. You go the inner one, then the middle one, then the outer one, and you're done. So this is integral 0 to 5, and this is just now 3 dy dz. And now single integral remains. It's a 3y from 0 to 5 dz. That's 15, so 0 to 2 of 15 dz, which is 15z from 0 to 2 is equal to 30. That's why. Obvious. Obvious. Now, again, if you have the rectangular region, you are allowed to swap integrals like this. Oh, by the way, I never mentioned for polar, we do not swap order of integration. It's r dr d theta, and that's the end of the story, right? For rectangular regions, yeah, we do swap them. And swapping here, it's fun. So for rectangular region, again, put them in any order you want and just make sure that the proper limits follow the assignment of, maybe you want dx dy dz or dz dy, dz dx dy, whatever, doesn't matter, if they're all numbers. And it's only used to compute the box. That's that, right? Now what I can do is I can plug in some function in there to have some kind of temperature distribution, to have some kind of different density, right, situation, right? So all of these kind of things, yeah, we can figure things out from there. Now let's focus on the one that we actually are going to use to compute shapes, and that is going to be the triple integral on the general region. Triple integral over general region. And now we have the triple integral over region D of f of x, y, z dv is going to be, and now we have to pick. We have to pick one of these. We can't do all of them, so we'll use the same one in the book, which is dz dy dx. So I have my triple integral. I still have the function x, y, z, and then we're going to put dz dy dx. Okay. I am going now to first put the values. This is going to be x1 to x2, y1 to y2, z1 to z2, where these y and z's are actually functions. Now let's see what are functions in terms of. So first of all, dx, right? That's going to swap from a to b, so I am replacing x1 and x2 with a and b. I'm going to replace all of them, obviously. So that's dx. We know that the outer integral must have a and b to compute the number, which is the volume at the end, like 30, right? So it has to have the outer integral. The outer integral has to have 30 as the result, or whatever number. So we have to have the numbers on the first integral. Now we're moving on the inner integral. function y is only allowed to be a function of x because z are already integrated out. So y is a function of x. So this is where we are going to use from g of x to h of x. And the outer function z is the function of x and y. So that's going to be capital G of x and a y and capital H of x and a y. So as you can see, there is a methodical way to build this. Trying to see if I can find a good picture that will use examples over here. Something that would illustrate this well. Well, they have only one, and if you don't understand this, well, you're doomed. Where's my... Here. That's where it goes. All right. Behold the shape. The orange, yellow, whatever the hell this is. And the blue. I know that's blue. Wait, it's blue. So now that's the shape. That's the entire shape. There's nothing else, right? It looks like a pill or something, right? It's round, so this could be a circle or an ellipse. When you shine the light from above, it would cast this kind of shadow on the xy plane. So now, what is the goal of the triple integral? Goal of the triple integral is to peek into the fourth dimension, whether it's temperature, density, whatever we are talking about. So, I need to deal with the shape of the object, right, in the limits of the integral so that I have my fourth spot over here for something. Remember, if I kill this, then it's just computing the volume. I can compute volume with the double integral, right? It's a big deal. I don't need triple integral to compute the volume. So we need this spot, which means that we have to stuff all of the qualities of the shape in the limits. Now, how do we do this? Well, we break stuff into parts. The most obvious part, I mean, it's obvious to me, is the top minus the bottom on the most inner integral. It's the z on the top minus z on the bottom. And that's these two functions, g and h, capital G and h, on ends. That's the top one, and that's the bottom one. Please remember from your Calc 1 and Calc 2, section 6.2, area between two curves. Wasn't it area of the, the top function minus the bottom function? And then you have the area in between, right? Well, same concept, shape on top minus shape on the bottom. And now instead of putting one minus the other, you put that into limits, because that's going to end up being top minus bottom, right? Because it's f of b minus f of a. So any time in the integral, when you have top minus bottom or right minus left, you can actually put the integral, even if you're already in 16 dimensions, no one cares, right? If you have a subtraction of the two, it can go into the integral on the limits. So the first step of the way is to realize what shape is on top, what shape is on the bottom, and those go top and bottom of the most inner integral. And then the tough stuff begins. Going the middle one is always the worst. I don't know, at least in my opinion, but then you might you might beg to differ and still say no. We have the domain, right? Because we shine the light, click, click, on the object. It casts domain in our xy plane, and that domain is going to fill in the other two integrals. So the blue and yellow, or whatever, are the caps, right, that do the inner one. Now we're moving on the inside. The outer integral, right, if it's dx, is easy because those are just the most left number on x-axis and the most right number on the x-axis, looking at the r. And then you have the shape of this. And that could be two functions, or it could be 0 and a function, or it could be, right, whatever it is. Now, this is what I'm going to do. I'm going to cover this middle integral over here, and when I cover the stuff in the middle, what you are supposed to see is the double integral for general region. That's exactly in your definition. If I kill the inner integral, which is top minus bottom here, it collapses back to double integral general region, 13.2. So whatever you have for 13.2, right, that's going to be the first two. Now we always know that the outer one is easy to find, and the one inside was pain in the neck because this shape could be anything, right? Now if this shape is circle, right, you are going from negative square root, blah, 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 to positive square root of blah, blah, blah. And that is when the other coordinates are going to kick in. We don't want circles in Calc 3 integral calculations. We want shapes like, you know, anything that is boxy, anything that is like a wedge, or maybe we want to figure out the skateboarding, bicycle, snowboarding ramps, and things like that. Things to figure out for roller coasters, and right? Maybe not roller coasters, that's too curvy. But, you know, the single ramp, you can break it up in pieces so it works fine. Whatever. So what is the perfect shape that, you know, we could consider to work on? Well, box, but I already did that, so yeah. A wedge, right there, right? This is not going to be a slice of cheese, because the slice of cheese would have over here curved, right? Because the cheese is a part of the big round, and when you cut out the slice like this is curved, like pizza crust, right? It's curved. So that would not be good for this, right? We do the double integral polar coordinates on that. This is a wedge, so all of these are planes that come together and create this shape. So now, how do you deal with this shape? Well, first off, we have top and bottom. Remember, those are the easy ones. What's on top, what's on the bottom. And as soon as you have flats, right? Flat floor, z equals 0. Flat ceiling, in our case, z equals 10. Over there, z equals 6. So those should be the easiest ones to get like this. Because generally, those functions are given to you, not for your egg. You'll have to figure it out when you trace your egg on the paper. But as soon as you're finished with that, right, trace your egg on the paper, you will be having the, right, and clearly if you trace your egg on the paper on a square grid, you will have some numbers to work with. So now, top and bottom, not a problem ever. Generally, those functions are given to you in a problem, and you just deal with that. The other stuff is the question, right? So what you do is you draw the base, the domain. I told you that 1,000 times. Draw the domain, and what you have in the domain is the triangle. And now that triangle is going to have, in a domain, is going to have dx dy situation, So, guys, as soon as you put z1, z2, top and the bottom of the inner integral z, the rest of the integral is your 13.2. General region in the bottom, and you have to figure out whether it's going to be dx dy or dy dx, and then use the same. So we are just adding one more dimension to 13.2 now. Now, as you can see, they did not draw the region, right? They did not draw the domain, so I have no clue how you're supposed to learn from here. Good luck with that. I'm going to do this problem and draw the region so that we are all clear how we get all of the integrals. So first, to draw the shape, we have our z-axis, we have our y-axis, and we have our x-axis. So we're going to go 0 to 2, and we're going to go all the way over here to 4, and then we're going to have a parallel line, let's say off of here, 2, 3, two, 3. Really? There we go. So this is just a wedge. And I have 2, 4, and this is where 0, 0, 0 is. That's all I need to know. I need to know that this is also 6. And that's that. Now what I'm going to do is I'm going to draw the domain on the side. And domain goes 2 in x and 4 in y. 2 in x and 4 in y. Domain. If you draw this stuff, you see it, it should not be an issue. So what do I have? I have a triple integral, and I'm not putting anything inside, so that's going to be 1. I know that the first one I want to be dz, and because that's dz, this is going to 0 to 6, because these are flat planes. Flat planes as the origin plane, right, the one you walk on, and then 6 feet ceiling. Now I'm going to put d and d. I'm not going to commit to xy or yx until I consider the domain. So you consider the domain, you look at the situation, and you immediately see that no matter which way you put it, it's going to be easy. Because if you put dx to be in charge, then dx will be going on the outer, y will be going on the inner, and dx swipes from 0 to 2, and dy goes from 0 to this function over here, y equals negative 2x plus 4. So negative 2x plus 4. So what happened here? Again, I use the power of the dx, representative rectangle. Representative rectangle has to start with its first value on the y-axis, and that's when x is equal to 0 for the limit. And then it's going to take all of the values on all the way to 2, which is the reason why dx goes from 0 to 2. Now dy is going to be the edges of the dx. You see that the top of dx always goes on a function, and the bottom of dx always goes on the 0, y equals 0, which is the x-axis. And then we already discussed 0 to 6. And all you need to do now is the integral in 3 layers, right? So this is like now 3 Calc 1 problems that you should be able to do. Now, you all know how good I am with this stuff, and you know, been doing this for very long, so it's obvious that the answer is 24. I mean, it's just clear. Clear like a day. Now, what I want to do is same problem in blue. Way 2, I am going to draw the same domain, but now I'm going to put dy. So now my triple integrals of 1 dz dx dy. Now z is still 0 to 6. That can't be changed because the bottom is flat, the top is flat, bottom is sitting on the xy plane, and top is a flat plane 6 feet up. Now I have to look at this. Now dy is in charge, and dy is going from 0 to 4. So the outer limits are 0 to 4. And the inner limits is going to be right minus left, so function minus the left, but that's a 0 in the denominator, right? In the denominator. And the lower limit, there we go. And I have to flip the function, right? I have to flip this function. That's 2x is equal to 4 minus y. X equals 4 minus y over 2. So now this blue integral also must equal to 24, because the previous one did. Now it's going to be your job to actually, when you start practicing this, right, compute both of these and make sure they both give you 24. Because they must. So I hope you see the way this is going to work. You will invest insane amount of time in sections 1, 2, and 3, and then the other sections should go somewhat quick because you already have all the basic ideas to work with this. So that is the problem that had a wedge. Let's see if we can find so the problem like this, that's going to be polar, all right? Why suffer? Why struggle? Why? When we can just flip it around and do it like that. So let's not worry about that now. Next section on Wednesday. And there it is. But before we go there, let's take a look at least one more homework example, maybe two. 850, right? You're all waiting for the homework to show up. So when you're computing triple integrals, you will do the same thing, like the inner one, then the middle one, then the outer one, and then either one of those could be U sub, partial fraction decomposition, integration by parts, right? Trig integral, trig sub-integral, right? If you have to do trig sub-integral, most likely you just need to change it to polar, okay? So, and if you need to do partial fraction decomposition in the Calculus 3, right, then just someone hates you. So pay attention. This is a cool application problem, right? I mean, it's done, so I don't need to do it. But example 5, average temperature, right? So they give you the region. The region is actually your object. So this region over here is the object, right? And you have the function that gives you the temperature distribution. So you integrate the temperature distribution here. dV. And, right? So find the average temperature of the block. They give you temperature distribution. Guys, it's never uniformly distributed, right? If you apply heat here, well, the hottest is going to be here, and you can still hold it, right? While there is a 2,000 degrees on this end, it takes time for that heat to disperse. So it's a distribution, right? And it's given by some kind of function that progresses through time and space. Ah, there they are. Basic skills. Skip right through that. More basic skills. Ah, not so basic skills. Look at these beautiful things. Look at 16. This is stuff that excites me. Look at 16. Wow. Shall we? Right? Yeah, why not? Epic. Let's draw this. Problem 16. We have our XY coordinate system, XYZ, and we are going to go to the point over here, call it pi, and then we are going to go about that amount. Call this point over here pi pi 0. That 0 means that it's a 0 on Z, which means it's on the floor. Connect this into a triangle. And then draw the top. There we go. The surface on top is Z equals sine Y. And that's all we need. They are giving you this side, equation for this side, but I'm not, because it's not necessary. Once you draw the domain, it will be clear what it is. So I'm not giving you that. This is it. Cool. You look at the shape, and you immediately realize that your domain is a triangle. You draw the domain. So origin is in the game. One of the points is there. We definitely go all the way to pi on y-axis. And then we also go to pi on the x, and we connect. So this is our region. Thank you. So this is our region. Now looking at this, region is so easy. I can do dy, dx, dx, dy. Doesn't matter. It's a nice region. Over here I see that I have this line on top, that it's y equals pi, and that is the equation they gave us. And I also have over here that y is equal to x. No, positive x, right? Yeah. Negative x would go this way. Good. So I'm going to use my beloved dx. And now set up the triple integral. Integral, integral, integral. Again, it's going to be 1 in here because nothing is given to us. And then we're going to have dz. And then I'll do dy dx because I already picked dx as my main. Now, this is volume equals, right? So the easy one is z, because it goes from the bottom to sine y on top. So that's what we have for z. What happened? Nothing? No. We're good? So now dx clearly goes from x equals 0 on the left to x equals pi on the right, and top and bottom and top go from x to pi. So 0 to pi, x to pi, 0 to sine y. And now we compute this quickly. 0 to x and pi dz. So when I integrate, that's going to be z from 0 to sine y. Dy dx still. Then we have still these two integrals. Plug in sine y, minus 0, that doesn't do anything, and then dy dx. The outer integral 0 to pi. Integral of sine is negative cosine y, computed from x to pi, and we still have dx. 0 to pi, we kick negative in front. I'm going to put negative 1 over here so it looks a little bit better. So 0 to pi, negative, right there, cosine of pi. So now when I plug in cosine of pi minus cosine of x dx. Now, how much is cosine of pi? Very good. So now I have negative integral negative 1 minus cosine x dx. And you see that I can factor the minus in parentheses, which kills the minus on the outside. Are we all green on that? So I can factor that. When I factor this sign inside the parentheses, this becomes 1 plus cosine x dx. And this is just x plus sine x from 0 to pi, and the whole thing is pi, right? Because sine x Sine x dies with 0 or pi. And obviously 0 in a polynomial doesn't do anything. So the only thing that is left is pi. Everything else is 0. Looked intimidating, right? But it's very structured, actually. But you have to unwrap 13.2 first. Because you will not be able to complete. Everyone in this classroom, without a doubt, remembered, oh yeah, bottom z, top z, right? Those are the pieces that keep the thing together, great. But these two, this is purely 13.2. You have to be able to put the domain down and then figure out whether dx, dy, dx, which one is better. Or maybe one of them is not possible. Now, to add a layer of difficulty to all of this, when this thing over here, right, ends up being evil, so it forces you to have a certain order over here. So that's another part. All right. Let's have you guys enjoy problem 23. So the cylinder, this cylinder has the x squared plus 4y squared equal 4. X squared plus 4y squared equal 4. And then you have two cuts, z equals 3 minus x, and z equals x minus 3. Go on. Calculate stuff.
Can we change the order of the dy and dx? Or like, is dz always in the middle?
You mean at the first.
Yeah.
All the way in.
Yeah.
Yeah. I mean, technically it doesn't have to be, but you would just make this problem so much worse by not doing it.
That was on Polar,
I saw
yeah, yeah, but X.
I saw like go onto the board one.
It's just explaining to me kind of it wrong.
Oh, I'm doing both. Oh, okay. I find it's too easy to
Okay, let's take a look at this. So we're looking at the problem 23. We have a cylinder that has been cut with two planes. And the shape of this cylinder is x squared plus 4y squared equals to 4. And we have two planes, z equals 3 minus x and z equals x minus 3. Now you can clearly see the z-intercept. This better be 3 and this better be negative 3, and then it's clear which one is which, right? Now we have a domain, and in order for us to understand the domain we have to divide by everywhere by 4, so x squared over 4 plus y squared equals to 1, because this is what the ellipse is. And from here we can see that our ellipse has 2 units in x direction and 1 unit in y direction, which creates our domain, which is this ellipse. So now I can put dx, dy, dx, we can't escape the ellipse. So I'm going to use dx as the main again. And I have to warn you, this object is not symmetrical. So you can't just say, okay, let me go from 0 to 2 and double it. We're going to go from negative 2 to 2 and negative 1 to 1, so we're all good there. Now, what's happening at the endpoints over here for dy? We have to solve this function for y. So y squared is equal to 1 minus x squared over 4, from where y is equal to plus minus square root of 1 minus x squared over 4. plus for the top, minus for the bottom. So what do we have? We have triple integral from negative, let's put all the stuff. So 1 dz, dy, dx. We put the z in because that's the easy part with this top and bottom. So I have the z to be 3 minus x on top. That has a positive 3. And x minus 3 on the bottom. That has a negative 3. So those are my z's. My x's are next. And that's negative 2 to 2. And again, do not use the symmetry rule because you might miss it. And now for the inner ones, I have a negative square root of 2 of 1 minus x squared over 4. And 1 positive 1 minus x squared over 4. And now all we need to do is to integrate this. Integrate 1, you get z, so you get a top limit, which is 3 minus x, minus the bottom limit, which is x minus, so plus 3. And we still have dy dx. So this is just 6 minus 2x. Dy dx. We still have the negative 2, negative square root, positive 2, positive square root. And now equal to... Now when I integrate in terms of y, these guys just get the y. So I'm going to keep 6 minus 2x as a constant and just put 1y to all of those. And I have a negative square root on the bottom, positive square root on the top. I still have integral negative 2 to 2 and dx over here. So now square root minus the square root is 2 square roots instead of y. So I get 2 integral 2 to negative 2 to 2. And then I have 6 minus 2x. And now instead of y, I have the top minus the negative bottom is 2 of those. So 2 times the square root of 1 minus something. X squared over 4 dx. And all we need to do is to integrate this. It's Calc 1, I mean Calc 2. So integral negative 2 to 2. I can... Well, let me first... I can factor out 4, if that's going to help. Kick out 4. We have 3 minus x times square root of 1 minus x squared over 4 dx. And the way to integrate this is to split into 2 integrals. So we have 4 integral negative 2 to 2, 3 square root of 1 minus x squared over 4 dx, minus, and let me just connect the minus, minus 4 integral negative 2 to 2 of x square root of 1 minus x squared over 4 dx. How do we solve the second integral? Anyone? U sub u equals 1 minus x squared over 4 du equals negative x over 2 dx. And then you just deal with that. How do we solve the first one? What do we do? For the first integral, we first write 12 integral negative 2 to 2 square root of, and then we factor out 1/4, which gives us 4 minus x squared dx. We kick 1/4 outside, becomes 1/2, so 12 becomes 6. How do we integrate this? Trig sub, yes. Trig sub. So we have the hypotenuse is 2, and one of the legs is x, the other one is 4 minus x squared, and then 30 minutes later, I mean, most of these problems are really good for carpal tunnel and killing time and things like that. So you guys can, you know, have fun when you wake up in the morning, nothing to do. 30 minutes later, hey, I made a mistake, and second line, minus sign, let's go back, redo it, because you want to. Good, that's that, 13 minutes ago. So, I will see you all in 2 days, and we'll do more. Bye.